Hello again, this is the course of data structure and algorithms, and in this video I would like to teach you about the binary search tree. Okay, it's not the PFS but it's the PST. Okay, and for this course the concept of binary search tree will be taught, and yeah, I will let you know some basic idea about insertion and deletion of the binary search tree and the performance. Okay, so we will check what is binary search trees. Based on the concept, these binary search tree are basically from the order maps. If you still remember maps, yeah. So if you are doing the maps, you will remember about the dictionary, and the dictionary in Python language, it consists of keys and items. So keys are assumed to come from a total order. It means you already learned in the maps. Okay, that we have the total order relation. Okay, so I hope that you can remember the mathematical concept about the total order relation. And we have items. So items are stored in order by their keys. This allows us to support the nearest neighbor queries. Nearest neighbor queries means that the item with largest key less than or equal to k, and item with smallest key greater than or equal to k. Okay, so if we have the order maps, it means yeah, we can easily to figure out which is an item that we want to rearrange. So let's see the binary search. Okay, I hope that you still remember the binary search. So something, maybe I need to put this one here. Yeah, if you still remember the concept of binary search on the first, or I remember the third or the fourth weeks of our lecture, so we learned the basic idea about the binary search. Yeah. The concept idea about the binary search is to perform the nearest neighbor queries on an order map that is implemented with an array sorted by key. Okay. So it's similar to the high-low children's game, and it at each step, the number of candidate items is half, and then it will terminate after log n steps. So yeah, you already remember, if you remember the one that we learned in week 4 or week 3. Okay. So let's suppose we have this number, okay, from 0 until 19. So we have this one, and we have the definition of low. Okay, and we have the definition of high, and then yeah, we want to find the mid value. Okay, so the mid value is the median. Okay, yeah, let's assume that we have this value in the odd numbers, and after we define the target number, let's say I want to find 7. Okay, what can I do with 7? So you need to find the, after you find the low, you find the mid, and then you find the high. Then you want to check whether 7 is in the lower of mid or the higher of mid. Because I know that 7 is lower than mid, then I will not, yeah, I will not check this part, because I know that 7 is less than the median value. So after I have this number, okay, I have this items for the next search, and again I will check whether 7 is higher or lower than the mid value. So the mid value is 3 here, and I want to know 7 is higher or lower than 3. Because I know that 7 is higher than 3, then yeah, we will not use the lower part, we just use those ranges of values. And yeah, I know that this is the H, and then this is the M, and then this is the L. Again, I have the M, and I would like to check whether the number or the target number is higher or lower from the mid value. after I check, then yeah, the number of 7 is the same with the low and it's the same with the high. So yeah, we can say that this is the number that you're searching. And if you do with all the numbers from the beginning until the end, so you can see there are n numbers: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So there are 13 steps to find the numbers. Yeah, it is the worst case. If you want to find 19, then the worst case will be, yeah, 30 numbers. But with this kind of idea, with the binary search, you can make it better. So there will be less than n numbers, which is the log n. So you can see here, we can find the number 7 with like 4 steps. If you start with the number 0, like 1, 2, 3, 4, 5, 6, okay, then will be 6 steps. So this is like all, yeah, not half, but it's almost half. Okay, so 6, if we have the with log n, and then with log n, okay, with the log n, we can get 4, something like yeah, almost half. Okay, so the search table that we are using, this one is implemented by means of the sorted sequence. So we can make a search tables with the sorted sequence. The items in the array base, it will be sorted by key, and we want to use the external comparator for the keys. As you might know, the binary search, the search function will take like O log n. So it will take O log n. And when we want to insert new items, it will take on. Okay? Because in the worst case, if we want to shift the items, then yeah, it will go until the n times. For example, if I insert in the first item, then I will remove all from the index 0 until the n. So that means that the insertion will take, the worst case is on. And removing item is also the same. It will have the on for the removal, because if I remove the element in the particular location, like the last element, then we need to change all. Sorry, if we remove the first element, okay, if we remove the first element, then you need to change all the values from the element 1 until n into 0 until n minus 1. So that's the idea. Okay. So the lookup table is effective only for order maps. So what is order maps? Order maps means you have the order keys of small size, or for maps which search are the most common operations. And yeah, insertion and removals are rarely performed. Yeah, for this one is on, so it takes more time than the log n. So using the order maps, it is recommended if you are going to search more than insertion and removal. Yeah. The idea of the sorted map is from the map that you learned before using the M. Yeah, actually, this chapter should be after we learn about the map, but they learn about the concept of graph and the shortest path. So I put this chapter at the last, and I think it's not that difficult to understand. And if you want to apply this operation, that's also fine, because I think it will not take a lot of time to understand whole concept, and especially it will not take a lot of time to implement with the Python code. So that's why I move first with the graph before I explain this section. So let's figure out more about the mk equal to v and the del. So there's those are the basic functions from the map, while the mk means I want to get the value. Okay, I want to get the value from the map M when the key go to k. Okay, so if that exists, then I can get the value. But if there is no such key, k is not exist, then it will be error. Mk equals to v means I want to replace the existing value of mk with the value v. And the del m key means I want to delete the key k in the map M. So we can do the sorted map ADD includes additional functionality guaranteeing that the iteration reports keys in sorted orders and supporting additional search like find greater than k or find in the range of start and stop. So some of the ADD, they have this kind of supporting search. Okay, and if you want to use those ADD, like the sorted map ADD, then you can just reuse it. In the binary search tree, okay, so we are doing with the search function with the order map, but when we deal with the binary search tree, that is a kind of different way. So the binary search tree is a binary tree. Okay, you know the binary tree means we have only two nodes. Okay, we have only two child nodes, and the binary tree is storing the keys or the key value items as its node and satisfying the following property. Okay, so this binary search tree is using this property u, v, and w, and let u, v, and w be three nodes such that u is in the left. Yeah, let's say u is in the left, and then v and u is in the left of v. Yeah, so let's say this is v. So we have u is the left of v, and then w is in the right of the tree. Okay, so if we have the u in the left and w is on the right, so we need to satisfy this property. So the u should be less than v, and the w should be greater than or equal to w. Okay, so this is the idea. Okay, so this is the concept. And the external nodes do not store items. Instead, we consider them as known. So external nodes, you know, the internal node and external nodes. So those are the external nodes. Okay, those are the external nodes, and there is no item for this one. In order traversal, if you still remember, in the trees we have several traversals. Okay, the in order traversal and post order traversal. Okay, and pre order traversal. So using the in order traversal of a binary search trees, it visits the key in increasing order. So we will visit this from 1 and then 2 and then 4 and then 6 and then 8 and then 9. Okay, so we call this is the in order traversal. So for the search, okay, when we are using this binary tree, it seems that this is a good way to search. Okay, so we are just searching the based on the k. So we have the key k, and then we trace a downward path starting at the root. And the next node visited depends on the comparison of k with the key of the current node. Okay, just read this one. If we reach a leaf, then the key is not found. So let's see. If I want to find 4, okay, if I want to find 4, then I would like to start from the root. Okay, so I would like to start from the root, and then I would like to check this one. I have T and then P and then K. So P means the something related with the map, and then K is the number that I want to find. So if I have the k equals to p dot key, then you finish or you already find. But if you cannot, if this condition is false, uh, if this condition is false, then you will go to the next. If k is less than p key, and the t left is not known, so it means we want to check the left one. If the k is less than the current node, so if it is 4, we want to find 4. So 4, I want to check with 6. 4 is less than or greater than 6, because we know that 4 is less than 6, then we will go to the left, and then we will do the recursion. So 3 search, and then the 3 is t, and then we want to go to the left of p, and then again we just put the k as the number that we want to find. Now after we have in this node, we will check again 4 compared to with 2. Is it the same with 2? No. And then I would like to check 2 and 4. So k, which is 4, is it less than the p key? So the key is 2. So 4 is less than 2? No. Then we will check the other condition. K is greater than p key. So k now, k is 4. Okay, 4 is greater than 2? Yes, because k is greater than 2, then we will do this one, which is to the right. Okay, so the t is the 3, and then t dot right p, so we'll go to this right, and then we can just give the number k and then do again. Now k equals to p key, 4 equals to 4. Yes, it's true. So we found the value. So the algorithms for linear algebra queries are similar. So we use this kind of idea to get the numbers. How about if we want to insert? So using the binary search tree, we can do this following procedure. Okay, to perform operation put k comma o, put, in the map you have the method put. It means I want to put the key k of the object. Okay, and we are trying to find out the way to save the key into the tree search. And let's assume k is not already in the tree. Okay, let's assume that k is not in the tree, and let w. Okay, so we have k and we have w. The w be known, and it will be the left reached by the search. Okay, so after we find the position, then we put the new node into that w. So we insert k at node w and expand w into the internal node. Okay, so let's see. Now I have this search tree at the original, and then I want to insert 5. How can I insert 5? So 5, I would like to check 5 is less than 6. Okay. 5 is less than 6. Yes. If it is less than 6, then we go to the left. If it is higher than 6, then we go to the right. Okay. Now, after we reach the 2, so I would like to check 5. 5 is less than 6. No. 5 is greater than 5. 5 is greater than 2. Yes, because 5 is greater than 2. Then, because it is true, we go to this one. Now, 5 compared to 4. 5 is less than 4. No. 5 is greater than 4. Yes, and we go to this one. So the position of the new node will be here. Okay. Then I will just put the new node, which is 5, and we create the external node for just this is the requirement. When you have the search tree, you need to have the external node which is none, or which is not no value. So this is the pseudocode of the tree. Okay, I guess it's the same with what I saw before. Oh, something wrong. I already did something with this one. Oh, but it doesn't change. Oh, this is the other one. Okay, so we want to remove this item. Okay, if we want to remove, we want to find the k. So k means the key that we want to remove. So first search the k, and then after I find the k, then I will try to remove. But we are not easily removing k with just delete, because we need to understand the other kind of condition after we remove. So assume key k is in the tree and let v be the node storing k. So if v has known left child w, okay, we can remove w and we can remove v from the tree with the operation remove external w, and it remove w with its parent. So let's see. I want to remove 4. Okay, so I have this kind of trees, binary search. I have the binary search like this one. So I would like to check 4. 4 less than 6? Yes, because 4 less than 6, then we go to the left. Now we will check 4 is less than 2? No. 4 is greater than 2? Yes. So we go to the right. And after we have this one, 4 equals to 4? Yes. Okay, then we want to remove this node. We want to remove this item, sorry, this key. And what we want to remove from this key is to remove including the leaf node. Okay. So after we remove this node, then the number 5 will go here because we just remove this key. Okay. Now we have another issues when when we want to remove the k and the node, it actually the children are both internal. Okay, so what does it mean? Let's say if I want to remove, we want to find the internal node w. Okay, so if it is internal, it means, yeah, like this one, we have the other children which has key. Okay. In the previous one, we easily remove this one because the node is the last node, or it is nearby the external node. But this one, this node is internal node. Then yeah, we first find the internal node w that follows v in the in order traversal, and then we copy the key w into the node v. Okay, so okay, let's follow this step first. And after we copy the key w into the node v, we remove node w and its left child z. It must be a leaf by means of the operation remove external z. So what does it mean? Let's see. I want to remove 3. Okay, I want to remove number 3, and then I will check 3 is less than 1. No. 3 is greater than 1. Yes. So we go to the right. And after we check this one, okay, 3 equals to 3. Yes, it's true. Now, the problem is if we delete this one, then we should do something with the left and the right. When we do something with this one, if we first we find the internal node, and next we need to copy the w. What is the w? So the w is the node that has leaf. Okay, so we need to find the node that has a leaf, and the node should be the next key after this key. So what is the next key after 3? Yeah, the nearest is 5. So we want to get the 5. Okay, so we want to find this node, the w that is following the in order traversal. It means the next node or the next key after 3. So we have 5, and then we want to remove this item, okay, because it is related with the Z is the leaf node, then I can say that the leaf node will be deleted and we will put 5 in this node. So the 5 will replace this position and the external node will be removed, okay, will be deleted, and yeah, the leaf node will replacing for the left child of number 6. Okay, so it means 5 will be not here, and then it will be the left node of number 6, and 5 will be in this node. Okay, so this is the case if you want to remove the node with children that is a node internal, if it is the internal node. Yeah. What about the performance? So the performance, I guess it's the same with the binary search tree that we already learned in chapter 7, I guess. Yeah. So when we have the order map with n items implemented by means of binary search tree of h8s. So let's see, we have this is the 8 is the height. So the space used is on, and then the search and update methods take oh. So at least there will be 8 times. So because it is the tree, okay. And the height 8 is on in the worst case, because yeah, if the tree something like this one, then it will just do the n times, and log n it will be the best case. Why? Because if the tree is something like this one, okay, so you don't need to check one by one. If you do this one, if the key is not here, then you will check the next. If the key is not here, then you will check the next. If the key is not here, you will check the next. If the key is not here, you will check the next. Okay, so it means it will take like n time. However, here, if the key is not here, you can check whether left or right. If it is on the left, then maybe yeah, this one. If it is not the key, then maybe this one. So it is lower in the time computational. Yeah, that's why the result will be log n. So this is the implementation. Okay, I don't want to discuss the details, so you can take a look on the code. There is the tree map, and yeah, this the thing that I already explained to you with the concept and with the examples for the binary search tree. Okay, so I will leave this code to you, and you can try to learn and understand the code. So I will discuss another things in different video. Thank you very much for listening.